Hello, welcome in the 9th lecture of two-phase flow and heat transfer. In this lecture, we will be learning about droplet annular flow and we will be later on discussing about stratified flow models. So, let us see the outline of the lecture. At the end of this lecture, we will understand the following points. We will be understanding the methodologies for generation of droplets from annular flow and how that transforms into droplet flow. We will be correcting the two-phase friction multiplier for calculation of friction factors, whatever we have given in your last presentation, that we will be correcting based on the presence of droplet in the core. In case of droplet annular flow, you will be finding out that the annuli is shedding some droplet and which is being carried in the core, right. So, that we will be actually changing the friction factor at the wall and accordingly the frictional force will be modified. So, those issues we will be tackling in this lecture. We will be also evaluating flooding limit for droplet annular flow based on reflux model. So, we know that there will be flooding by gaseous phase whenever there is very high velocity of the gas. Okay. So, in the extreme upside direction, whenever droplets are flowing inside the pipe, you will find out flooding can occur. So, we will find out that what is the limit beyond which flooding can occur from the droplet flow. So, for that we will be using reflux model, our earlier knowledge of reflux model, and at the end section of this lecture we will be discussing about stratified flow. We will be showing that how wave structure in stratified flow can be clubbed in horizontal orientation, and then we will be extracting the limits of large and small wavelengths. So, both the extremes we will be seeing the large and small wavelengths. Okay. To begin with, first we will see how droplet annular flow actually generates. So, we will start with annular flow, what we have discussed in the last lecture. We know in case of annular flow, around the in the wall of the tube you will be having liquid film. Now, here I have shown one side of the tube wall with which the liquid film is adhered. Okay. So, I have explained the gaseous flow in the core as Ug over here. Now, if you see that in magnitude the liquid velocity Uf is higher than Ug, then you will be finding out that due to the higher liquid velocity, there will be bulge formation in the film which is adhered with the wall. And as it continues further, you will be finding out that this film is forming a bag kind of thing over here for the air. Okay. So, air can accumulate over here inside that extrusion of the liquid, which will be acting as a bag, right. This continues to grow further and you can find out that there is a lengthy protrusion of the liquid film which further can pinch off at some point over here and form a droplet. Now, here we are having continuous flow of gas which will be carrying forward those droplets which are being formed along with it in the core. Okay. So, in this fashion inside the tube you will be finding out lots of droplets are being created of different size depending on the flow velocities, and you will find out in the core we are having lots of droplets, right. So, that is characterized by droplet annular flow. Next, another mechanism I will be showing you for which droplet is also created. Here you see we have started from similar configuration, we are having liquid film adhered with wall. So, this is this vertical line is actually the tube wall. Let us consider one half of the tube wall we have shown over here. So, here we are having the core gas flow characterized by its velocity Ug. Now, if we consider the magnitudes of the flow velocities are such that Ug is greater than Uf, then you will be finding out due to these flow velocities, okay, a fluid lamella is actually being sheared off by the fast moving gaseous stream. So, you can find out this lamella can pick up in length and you will be finding out that at some point of time whenever lamella length is becoming very high, there will be chances that surface tension will increase in magnitude, and you will find out that a small droplet can be shed off from that lamella. Okay. Now, this fast moving gas over here will be actually picking up this droplet and take it in the core. Okay. So, these two phenomena are actually important for generation of droplet from your annular flow. The first one we name as undercutting, okay, and second one is called rolling. Okay. So, these two phenomena are actually very important for generation of droplet annular flow. Now, to characterize that what amount of droplet you are having in the core, we define a parameter called E. Okay. So, this E is actually the ratio of droplet flow rate in the core. So, whatever volume of droplets you are having in the core or mass of droplet you are having in the core, because density is not going to change. So, that we find out over here droplet flow rate divided by total liquid flow rate. So, total liquid flow rate will be actually your droplet flow rate plus whatever film we are having over here with the wall adhered with. So, that flow rate also will be coming into picture. So, this total liquid flow rate will be your film flow rate plus the droplet flow rate. So, the ratio between these two is actually called E. So, E can be 0 whenever you are having a perfect annular flow. Okay. That means there is no droplet in the core, right. And in case of your droplet annular flow, you will be finding out that E is lying in between 0 and 1. Usually, typically you will find out that this E value will be definitely less than 0.15. Okay. Next, let us see that how this ratio of the volumes, droplet volume and the total liquid volume can be found out. Okay. So, there are number of correlations available for this, but best suited correlation has been given by Ishii and Mishima in 1982. What they said that this E can be characterized as tan high parabolic of 7.25 into 10 to the power minus 7 Jg to plus. So, this is not Jg, this is modified Jg actually, I will be telling you next. So, Jg plus to the power 2.5 into D plus to the power 1.25. So, this is also modified diameter or non-dimensionalized diameter we can say, multiplied by Ref. So, this is liquid Reynolds number, modified version of liquid Reynolds number. No, this is liquid Reynolds number actually. So, Ref to the power 0.25. Okay. So, let me quickly explain that what are these terms Jg, D and Ref. So, Jg plus you can write down, this is actually a non-dimensionalized version of Jg. So, it is Jg multiplied by rho g to the power 4 by 3 divided by sigma into g rho f minus rho g to the power 1/3 whole to the power 1 by 4th. So, this is actually giving you the unit of meter per seconds meter per second, and this is also meter per second. So, you will be finding out they are cancelling out and this will be a non-dimensional number. Okay. In a similar fashion, D plus can be written as D multiplied by G into rho f minus rho g divided by sigma. So, this terminology, this numerator and denominator, they are coming from the balance of your buoyancy force and your surface tension force. So, we are non-dimensionalizing the diameter of the tube by this non-dimensional length square, half to the power half of that will be coming into picture for non-dimensionalizing the tube diameter. So, D plus is equals to D into this one. Okay. And all of we know that film Reynolds number will be nothing but rho f into Jf into D divided by mu f. Okay. So, all the fluid properties will be taking into picture. So, once we know, you see in this expressions all the values mostly are from fluid properties, only D is actually your from your system whatever pipe diameter you are having, and Jg will be dependent on your Ug. So, you can find out once you know the flow parameters and the velocities, you can find out what is the value of E. Okay. So, the ratio between the droplet mass and the total liquid mass you can find out in case of your droplet annular flow. So, that is why this correlation is very important. Okay. Next, in the last lecture we have talked about that how to calculate the friction factor for annular flow, and there we have seen that two phase multiplier phi will be very important. Two phase multiplier phi g square will be very important. So, here I will be showing you whenever we are having droplets in the core of the annular flow, how the values of phi g square will be changing. Okay. And once you calculate the phi g properly, so your calculation of the frictional force will not be difficult, and the approach for finding out the friction factor using phi g square already I have shown you in case of your homogeneous or separated flow models. Okay. So, let us try to see how this phi g square is changing with respect to the presence of droplets. So, here we are considering that we are having entrainment. By the way, this liquid whatever it is coming in the gaseous phase, liquid droplets, those are called entrained droplets. So, let us see that what is the effect of liquid entrainment, okay, on the pressure drop, that means on the frictional pressure drop. So, first we will be trying to explain what is the interfacial shear stress tau I. So, tau I we have earlier shown that this will be half F into your rho g into u g minus u I whole square. Earlier all those i's were replaced by u g's. So, this was f g, this was rho g, and this was u f. Okay. So, now here in the core what we will be finding out, it is not only the gaseous phase, we are having liquid droplets also. So, the core density if you try to find out, this will be not essentially the gaseous phase density, this will be modified by the liquid entrainment. Okay. So, that we need to take care of. So, here what we have written that what will be the core density now, rho CO. So, rho CO in ideal case, annular flow case, that will be definitely equivalent to rho g, but as we are having droplet entrained in that. So, what we are doing over here, we are increasing the density by some factor which is nothing but W g plus E into rho f by rho g. Now, it is very good factor to add. Why? Because if E is equals to 0, then you will be finding out that rho CO is becoming rho g. That means, if there is no entrainment, then you will be finding out it is becoming rho g. Okay. Now, once we have found out this rho CO, next task is to assess what is the value of interfacial velocity, that means W I. Okay. Now, for this derivation I am considering that u I is known to us, and that is equivalent to 2 into u f. U f is essentially the liquid velocity. So, this is the assumption. So, if you are having some another value of u I, accordingly you need to change. I have taken this one as 2 into u f just to simplify our calculations. Okay. Now, you see, if we add all these things in this expression of tau I, the tau I will be changing to half into f I rho CO into u g minus 2 u f whole square. Though I have not placed this rho CO expression from here to this one, but one can do that one. So, now I am interested in this u g minus 2 into u f whole square part. So, I will be explaining that one separately. So, please remember that whatever I will be deriving now from now onwards, this half f I rho CO will be coming as multiplier to that. Okay. So, here you see rho g minus 2 u f u g minus 2 u f whole square, what we can do, we can take common u g square. So, it will be 1 minus 2 into u f by u g whole square. Now, all of we know, and we have also shown you in the first lecture, that u f by u g can be written as 1 minus x by x into rho g by rho f into alpha minus alpha by 1 minus alpha. Okay. In the first lecture, introduction lecture, I have shown you the proof of this one. So, we can replace u f by u g by this expression, right. Now, next as we are having over here 1 minus mass quality by mass quality. So, what we can do, depending on the whatever masses we have in the core and the wall, we can replace this mass quality by the liquid mass flow rate and the gaseous mass flow rate. So, we will be finding out over here liquid mass flow rate adhered with the wall, we will be W f into 1 minus E. So, because W f into E portion is always with the core. So, that is why we are writing W f into 1 minus E, okay. And obviously, W g will be remaining same. So, here we find out that u g minus 2 u f whole square becomes this full expression. So, what we can do for finding out tau I, we can hook this expression with the multiplier half Fi rho CO. Okay. So, let us see that. So, if you proceed in this fashion, already in the last lecture, if you remember, I have shown you based on Wallis correlation that phi g square can be written as 1 plus 75 into 1 minus alpha by alpha to the power 5 by 2. Okay, where you know Fi is not equals to FTP, Wallis has given some correlation, and based on that we have explained this one. So, what we will be finding out that with this gas entrainment in the core, you will be finding out that along with this term there will be one multiplier. That multiplier is nothing but essentially this multiplier whatever you have. So, we will be finding out over here 1 minus 2 into Wf into 1 minus E by Wg into rho g by rho f into alpha by 1 minus alpha, whatever I have shown you in the previous slide. Along with this, what is this? This is nothing but your rho CO value. You see rho CO I have already shown you over here, rho CO is Wg plus E into Wf by rho g. So, that multiplier will be coming also over here, because rho is changing, rho g is changing to rho CO, and your Ug square which was there earlier in the Wallis criteria, that is changing to Ug minus 2 Uf whole square. That means this whole expression. So, these two terminologies will be coming as multiplier over here with the phi g square. So, in this way phi g square can be modified based on the knowledge of E. Okay, E once again how to calculate I have already shown you. So, based on the knowledge of E, you can modify this phi g square value and calculate the pressure drop accordingly. Okay. Next, let us move to the flooding criteria. So, as we know that we are having we are moving towards the droplet flow. So, what we need to do? We need to find out that what is the flooding condition or limit given for the tube. So, what we will be following over here, we will be following one correlation given by Wallis once again. So, what he has mentioned Jg star to the power half plus m into Jf to the power Jf star to the power half is equals to C. Once again, if you remember, this is actually coming from our difflux model, where we have shown that some multiplier into Jg plus another multiplier with Jf is equals to constant, which is a straight line manner, and we have shown some examples also of pipe flow, adiabatic pipe flow, where we have found out the operating points using Jg and Jf value. So, similar type of equation Wallis has also proposed over here, but what he has done over here, in place of Jg and Jf, he has given some non-dimensionalized Jg and Jf to make it generalized. So, let us see what is Jg star. Jg star is actually involving Jg, and then he has actually multiplied rho g to the power half divided by Gd multiplied into rho f minus rho g to the power half. So, as he has included this diameter and the density is fluid density, so it will be valid for any fluid pairs and as well as your pipe diameters. Okay. Similarly, Jf he also defined. So, Jf star is nothing but Jf into rho f to the power half Gd rho f minus rho g to the power half. Okay. So, this is a very important criteria. So, using this equation you can find out for a given value of Jf what will be the value of Jg, so that you can avoid flooding. Okay. Now, very important thing over here in this correlation to find out the value of M and C. So, Wallis has suggested that C will be lying in between 0.7 to 5 to 1. So, this will be depending on the pipe material, whatever material you are having, as well as it also depends on the pipe diameter. So, you have to pick up. So, he has given a chart actually for picking up the values of C in his research paper. So, one can pick up the correct value of C by knowing the condition of your experimental setup and evaluate the value of C. Now, the rest part whatever is remaining is actually M. So, let us see how M can be found out. So, what Wallis has mentioned, he has actually given two curves like this, okay, for finding out the value of m and c once again. So, what he has related, he said that this both this m and c, they are actually dependent on your non dimensionalized inverse viscosity, what we have defined in case of your dispersed flow models. Okay. So, this once you know the fluid properties, definitely you will be finding out the non dimensionalized inverse viscosity, and once you know the viscosity, so using these two curves you can find out the value of m as well as you can find out the value of c. It is interesting to note that up to certain limit of non dimensionalized inverse viscosity, the value of c remains constant. Okay. After that it takes some variation. So, you have to take the values of m and c accordingly, right. Wallis has also proposed that if you are having a short pipeline, that means the droplet annular flow is happening in a short tube. So, in that case you can go for simpler value, because finding out m and c in this manner is little bit tedious. So, you can go for very fast hand calculation, short calculation by taking m and c is equals to 1. So, that means essentially it becomes jg star to the power half plus jf star to the power half is equals to 1. So, which is the equation of straight line having 45-degree inclination. So, if you see, I have shown here that curve, that this is nothing but your jg star to the power half and this is your jf star to the power half. So, if you plot, this is a 45-degree line. Okay. So, below this you will be finding out that droplet flow can exist over there. Okay. And if you go beyond this one, that means keeping a liquid velocity same, if you go for higher gas velocity, you will be leading towards flooding. So, this type of curves are very helpful for finding out the flooding limits. Okay. Next, let us move our to our next part, where we will be mentioning about stratified flow. So, stratified flow, all of we know that is a part of your horizontal channel, and you know that in case of horizontal channel we will be having well stratification between the liquid phase and the gaseous phase. So, here I have shown a figure where you can find out liquid phase is flowing at the bottom and gaseous phase is flowing at the top, right. So, to show the velocity vectors over here, we have shown that in case of gaseous phase there will be higher moving velocity compared to liquid part over here. So, that means in case of two phase, your parabolic velocity profile exactly will not be valid. So, you can find out the maxima of the parabola has shifted towards the upward side. Okay, but there will be no discontinuity of velocity at the interfacial point. Okay. So, if we consider that one, in some cases people consider the slip, but here we are not considering that slip. Anyhow, so here rho g and ug are the corresponding density and velocity for the gaseous phase, and rho f and uf are the corresponding velocities for the velocities and densities for the liquid phase. Now, what we will be doing over here in this stratified flow, we will be imposing the waves. Okay. So, all of we know that let us say this is the unundulated stratified phase interface, okay, somewhere lying over here, okay, at a height of hg for the gas and hf for the liquid, whereas total height or the channel length is actually channel height is actually h. Now, if you impose the wave over here, okay, let us take the waves equation is eta xt is equals to eta max into e to the power I k x minus ct, where we know that in this type of waves k is actually the wave number represented by 2 pi by lambda, where lambda is the wavelength, okay, and c is the wave velocity, okay, and eta max can be the maximum wave amplitude. Okay. So, if we impose this wave, so this will be looking like this. Okay. So, let us try to assess that what happens if we impose this wave on this non-undulated structure of the stratified flow. So, first if we want to calculate the wave speed, we will be taking one important work done by Weda. He has given in 1968 that this wave velocity can be approximated as rho f uf if plus rho g ug ig divided by rho f uf plus rho g ug plus minus root over of you are having sigma k, which is the wave number, plus rho f minus rho g into g by k once again divided by rho f if plus rho g ig minus rho f if rho g ig into ug minus uf whole square divided by rho f if plus rho g ig. So, this is actually your equation of a quadratic nature. So, from there the roots he has found out. Anyhow, so we will not be going detail of that one, but using this one we will be trying to prove the extreme limits. So, here by the way I have not mentioned the IF is nothing but your cot hyperabolic of wave k into HF, where HF is the height I have shown in the previous figure, and Ig is equals to cot hyperabolic of k into Hg. Now, if you first try to find out what is the unstable flow condition. Unstable flow condition means as the wave we are imposing on the stratified flow. So, if the wave is very unstable, so then there will be chaotic situation inside the pipeline. So, to check that we have found out what is the unstable flow condition. So, for unstable flow condition definitely the wave velocity will become imaginary. So, for making it imaginary we know if we are having something under root negative, then that will be imaginary. So, the limit we will be finding out this one is equals to 0. So, if we make this one is equals to 0, from there we can get what is the relative velocity ug minus uf. So, that ug minus uf by making this one is equals to 0 will be coming as rho f if plus rho g ig by rho f if rho g ig multiplied by sigma k plus rho f minus rho g into g by k to the power half. Okay. So, this is very important equation. Okay. Next let us see the extreme limits. So, first one what we will be showing you hf by lambda and hg by lambda, that is higher than 0.25. That means the wave is very steep. Okay. So, the amplitude is small, but the wave is very steep. Okay. So, the height is actually very big compared to this lambda. Okay. So, let us see now what is the consequences. So, if you see already I have shown you that IF and IG is cot hyperabolic of KHF and KHG. So, if HF and HG they are very big values, then you will be finding out that this IF and IG will become nearly equals to 1. Right. So, if I put these values of IF and IG once again back to the limiting UG minus UF, then you will be finding out that UG minus UF becomes rho f plus rho g divided by rho f rho g multiplied by sigma into k plus rho f minus rho g into g by k to the power half. It is interesting to note that in this equation still we are having the wave number value k. Okay. So, let us try to find out that for what amplitude this relative velocity becomes your minimum. Okay. So, let us try to differentiate this whole equation with respect to your lambda. So, if you do so, then we will be finding out del lambda of this part is equals to 0 for the minimum velocity, because these are constant terms. So, this will not be coming into differentiation. So, eventually this differentiation of this will be giving us the minimum conditions. Okay. So, once we do the differentiation we will be getting that minimum lambda comes out to be 2 pi root over of sigma by rho f minus rho g into g. Okay. So, this is the minimum lambda for which you will be getting the stable solution, okay, at minimum velocity. Okay, now, if we put this value of lambda mean once again back to UG minus UF, then you will be getting expression like this, that UG minus UF limiting is equals to root over of 2 into rho f plus rho g by rho f into rho g into sigma rho f minus rho g into g to the power 1 by 4. This is very easy to calculate, just you put the value of lambda mean over there in place of 2 pi by lambda, and here 2 pi by lambda, you will be getting this equation. Okay, now, here if you keep negligible surface tension, okay, so surface tension is very negligible, then you will be finding out that this UG minus UF will be turning out to be this one. Okay. So, here you will be finding out that in this we are not having surface tension. So, let us take this equation. So, over here if you nullify this surface tension value, so let us say it is not surface tension is not there. Remember, this is not for the minimum velocity, this is only for the no surface tension case, then you will be finding out UG minus UF is equals to this factor rho f plus rho g by rho f rho g multiplied by this one. Okay. So, that same thing we have found out over here. Okay, let us see the another extreme case. So, if we are having rho f by lambda and hf by lambda and hg by lambda is less than 0.1. Okay, that means you are having a very long wavelength. Okay. So, in that cases you will be finding out that IF and IG those are turning out to be 1 by KHF and 1 by KHG. So, essentially that is lambda by 2 pi HF and lambda by 2 pi HG. Okay. So, let us do one thing, put these values of IF and IG back in the UG minus UF. So, if you put this value UG minus UF over here, so I will be finding out that once I put these values, this will be simplifying, okay. So, and it is very interesting to note over here that here we are having k to the power half and here we are having 1 by k to the power half, and eventually UG minus UF will become one expression involving sigma rho f rho g g, but interestingly there is no lambda value over there or wave number value over there. So, this is irrespective of any wave number, okay. Now, if you go for negligible surface tension, so make this surface tension 0. So, you will be leading towards Hg by rho g plus Hf by rho f into rho f minus rho g into g to the power half. If you remember your knowledge of fluid mechanics, this is very typically the expression we see in case of Kelvin-Helmholtz stability. So, basically for long wavelength that will be dominated by Kelvin-Helmholtz stability, right. So, let us summarize this lecture. In this lecture we have considered droplet flow rate and shown the modifications of the frictional pressure drop. We have correlated flooding limit, okay, and highlighted its empirical constants, and we have also shown you how empirical constants can be found out. We have found out the wave formation in stratified flow, okay, and discussed what are the wave number value relationships, okay, and physical properties involved in that. And at the end we have seen the extreme limits for the wave amplitudes, that means maximum and minimum extreme amplitudes, okay. So, those things we have seen and found out that whether it is dependent on the surface tension or not, okay. So, with this let us test your understanding after the end of this lecture. So, first question goes like this: flooding limit in a droplet annular flow depends on 4 answers we are having: surface tension, viscosity, tube material and tube diameter. So, I think all of you have guessed the answer. It is viscosity and tube diameter, because in the expression if you see we are having mu as well as a capital D. Okay. Next question, undercutting is significant in following conditions. In the first slide I have shown you, so probably it is very easy to get the answer. So, we are having 4 answers: Ug greater than Uf, Ug less than 0, Uf greater than Ug and Ug equals to 0. So, correct answer is the answer C. Next, in stratified wavy flow, relative velocity will not depend on wavelength. Mention correct assumption for approaching the statement. We are having 4 answers: negligible surface tension, same viscosity, negligible shear stress, and fourth one is negligible buoyancy. So, the correct answer will be negligible surface tension. So, with this I will be ending this lecture. Thank you.